Welcome to our fifth lecture. Today we will talk about sources. Let's start with the ideal voltage source. We used it already and now let's have a closer look. What happens when we connect a load resistor to our ideal voltage source? Then a current would flow and we would have a voltage drop here. And now let's figure out what the output behavior of our ideal voltage source would be. It's quite easy because it's an ideal source. We will always have the same voltage drop U0 at the clamps, and it doesn't matter which current flows. Let's do an experiment. I do it with a simulation program because it's easier to see what happens for you. So I have a voltage source there, and this voltage source is a battery. And our left measurement device measures the voltage and it's 1.5 volts. And then I have a load circuit there. There are 3 switches and I can switch on up to 3 lights. And our second measurement device will measure the current that flows through our lamps. Okay, let's start. So we have now 1.5 volts at the battery and there is no current flowing. And now I switch on the first light. And now you see there is a current flowing, but you also see the voltage decreased. We only have 1.35 volts left. Let's switch on another lamp. You see the current increases, but the voltage decreases again. Let's switch on the last lamp. And again, the current increases, but the voltage decreases. That means our battery is definitely not an ideal voltage source. But how could we model that? Okay, we've seen that an ideal voltage source is not a good model for a battery or for any other source because real sources are not ideal. So what could we do? I will show you. We can just model our source like this. We add an inner resistor and now let's have a look what happens when we connect a load resistor. Then again a current would flow and we would have a voltage drop here. Okay, but there will be a voltage drop at the inner resistor and this voltage drop is dependent from the current which flows out of our source. And now we can calculate the voltage at the clamps, so the output voltage of our source can be calculated with Kirchhoff's voltage law, and it looks like this. Okay, let's draw this. When no current flows, you see it in the equation, then we just have U0. And we call this the open loop voltage because when no current flows, it means that the clamps are not connected to anything. So we call it open clamps and the voltage drop there is the open loop voltage. Okay, and from our equation we see that with increasing current the output voltage is decreasing. So it will look like this. Okay, and the point there where no voltage drop is left. We get this point if we make a short circuit at the clamps. With a short circuit we have no voltage drop there, and we can calculate the current flowing then, because all we have from our circuit is our ideal voltage source and our inner resistance. And that means we can calculate it with Ohm's law. It's just U0 divided by Ri. Okay, let's do the same for our current source. We again begin with our ideal source. If we connect a load resistor here, a current would flow and we would have a voltage drop. And it is an ideal current source. That means it doesn't matter what voltage drop we have, we will always have the same current flowing there. Okay, and guess, we don't have ideal sources. That means we have to add something to get a practical source. And again, it's the inner resistor. And if we connect to our practical current source a load resistor, then again a current would flow here. And again we will have a voltage drop at the clamps, but at our inner resistor is that voltage drop, and that means that a current flows here, and according to Ohm's law it's this voltage drop divided by the inner resistance. And now we can use Kirchhoff's current law to calculate the output current, and it looks like this. Okay, let's draw it. When we don't have a voltage drop, that means we have a short circuit at the clamps. Then we will just have our short circuit current at the clamps. And when the voltage increases, we see from our equation the current decreases. So we have again this diagram here. And in the end, in that point, there is the current at zero. Zero current, that means that nothing is connected to the clamps, and therefore all the short circuit current flows through the inner resistor, and that produces a voltage drop of Is times Ri. Okay, I've shown you two different practical sources, the practical voltage source and the practical current source. And the practical voltage source has this output characteristic, and the practical current source this one. They are identical. The only difference is that I used in the left diagram the current on the x-axis and the voltage at the y-axis, and it's other way around in the right diagram. But the behavior is absolutely the same. And when the behavior is the same, then we can transfer a practical voltage source into a practical current source. I will show you how it works. It's very easy. The very good news is the inner resistance is the same in both sources. So just use the old value and put it in the new source. And if we start with a practical voltage source and we want to create a practical current source, we need the short circuit current. And the short circuit current is when we make a short circuit at the clamps. And on the left side at the practical voltage source, the current that would flow there is the open loop voltage divided by the inner resistance. And therefore, it's just Ohm's law what we need. When we have a practical current source and we want to have a practical voltage source, then we need the open loop voltage. Open loop voltage means that we have not connected anything to the clamps. That means that in our practical current source, the short circuit current flows through the inner resistor and makes a voltage drop of Ri times Is. Again, it's just Ohm's law what we need. You might wonder now where you should use it, and I will show it to you. I have an example circuit here, and I want to transfer this circuit into a practical source. A practical source has only two elements, an ideal source and the inner resistance. And the output characteristic of our original circuit, output characteristic means that the behavior to the outside world when we connect something to the clamps will be the same in the original circuit and in our practical sources we create from this circuit. Okay, let's have a look. When we have a look at the circuit, we could say, hey, here is a practical voltage source, an ideal voltage source with a resistor in series. And we could transfer it into a practical current source. It looks like this. So this here is our practical current source generated from our practical voltage source. And yeah, the value would be 1.5 amperes. And now we have two resistors in parallel in our circuit. We could combine them. And now we have a practical current source there. It's the 1.5 ampere ideal current source and the 5 ohm resistance. We could transfer that into a practical voltage source. So it leads to a practical voltage source with the open loop voltage of the 1.5 amperes times 5 ohm, and the inner resistance is 5 ohm. Okay, and now we have two resistors in series and we can combine them. And if we do so, we are finished with our practical voltage source. And this voltage source had the absolute 100% same behavior to the outside world as our original circuit. But our original circuit has 4 elements, and our new circuit has only 2. And the cool thing is, this tool works for huge circuits, and you can combine a huge circuit with 2 output clamps into a practical source, and it just behaves the same. Okay, now we have a practical voltage source, and of course we can transfer it into a practical current source if we want. I prepared another simulation for you. We have 3 circuits. In the yellow boxes we have in the top our original circuit. In the middle we have our practical voltage source, and then we have our practical current source. And I said that all 3 circuits should have identical behavior. What we also have are ideal measurement devices, so we measure the output voltage of all 3 circuits and we measure the current which flows out of our circuits. Okay, and here we have a load resistor network, and if I close the switches here, then I can connect resistors to our source networks. Okay, so we see now we have open clamps here, and we have 3 times 7.0 voltage drop at the output clamps. And now I switch on our first load resistors. This one, this one, this one. And now you see our 3 different circuits have absolute same behavior. Now the voltage drop at the clamps is 3 volts, and we have 300 milliamperes of current flowing out of the networks. Okay, let's add another resistor. So you see, the current increases, the voltage decreases, but the behavior of all three circuits is the same. And last case, and again, the three voltage drops at our clamps are identical and there is the same current flowing out of every network. Okay, so you see our three networks have absolute same behavior to the outside world. Okay, we've seen that we can transfer a given circuit step by step into a practical source. But there is another way, and this way is valid for both, for calculations, but also for measurements. I already told you that you can transfer a circuit into a practical source. And this works for all circuits consisting out of ideal sources and linear elements. We know up to this point the resistors, but inductors and capacitors work too. Okay, and if we use our method to create a practical voltage source, then this method is called Thévenin's equivalent. And if we use it to create a practical current source, it's called Norton's equivalent. So if we have a circuit given, we can calculate or measure the open loop voltage. And this voltage is the voltage of our practical voltage source. Or we could measure or calculate the short circuit current. That means we make a short circuit at the clamps and measure or calculate which current flows there. And the last element we need is the inner resistance, and we can either calculate it. If we have open loop voltage and short circuit current, we can just calculate it with Ohm's law, or we could measure it or calculate it, and therefore we have to deactivate all the sources in our circuit. Okay, what does it mean to deactivate a source? Yeah, if you have a voltage source, it just means that it becomes a short circuit. And if we have an ideal current source, it becomes an open circuit. Okay, let's use our example again. I want to transfer our circuit into a practical voltage source. So we need this voltage here. And on this point, you should be able to see it if you made your trainings. So the voltage drop here would be 7.5 volts. Now we need the inner resistance, therefore we deactivate the ideal voltage source and we look into the circuit from the point of view of the clamps, and we see that the inner resistance is, you should see it, 15 ohm. And therefore our practical voltage source looks like this. Let's have a second example. It's the same circuit again, and this time I want to create Norton's equivalent. So I want to create a practical current source. Therefore I need the short circuit current. So we make a short circuit here and we measure or analyze which current flows there. And again, you should be so trained now that you can see it. If you don't, practice more. So the current here would be 0.5 amperes. And we also need our inner resistance, but it's the same as before. We deactivate the source, we look into the clamps and see, hey, the inner resistance is 15 ohm. And then we have our practical current source and it looks like this. So, and here's the last experiment for today. We have here our example circuit 3 times. In the first circuit here, I will measure the open loop voltage. So this is an ideal voltmeter. In the second circuit, I have an ideal ammeter here. It behaves like a short circuit, so we measure the short circuit current here. And in the last circuit, I deactivated the ideal voltage source, so it became a short circuit. And here I have an ohm meter, and we will measure the inner resistance of our circuit. Okay, and now let's start the simulation program. And you see, we again have the same values. We have an open loop voltage of 7.5 volt. We have a short circuit current of 0.5 amperes. And we have an inner resistance of 15 ohm. So you see, we can create our practical voltage source or our practical current source either with calculations or even with measurements.